Good evening. This is Math 2414. Today is January the 29th. A couple of announcements to start off our lecture today. First of all, the next homework assignment will be due February the 4th. I'll be making an assignment at the end of class today or at the end of the lecture, and then again at the end of the lecture on Wednesday. Remember, I will identify the homework that's to be turned in by section number and not by page number, because the page numbers in my hard copy book apparently are wrong. So just be looking for that at the end of the lecture today and again at the end of the lecture on Wednesday. Thank you for all of you who turned in your homework assignment to me before the end of the day yesterday. That was great. I saw most people turned it in. Remember, I will drop a grade or two at the end of the semester. So if you missed one at the beginning of the semester or sometime during the semester, it's not going to hurt your grade. But don't get behind on that. Don't start mounting up zeros in the homework, because then that will hurt your homework average at the end of the semester, and you want that to be a good grade. There's no reason why that shouldn't be a good solid A for the semester, because I'm only going to be assigning 2 or 3 problems a week that are to be turned in. So that should not be too big a deal to do well on that. And remember, you can always come by my office for help if you want it. So also, let's see, exam 1, the review will be posted by Thursday of this week. I've started on the review, and I'll be finishing that review up in the next day or two, and I'll be posting it by Thursday of this week. The window for taking exam 1 is February the 8th through the 13th. I will be on campus on February the 7th and 8th, and I will always come onto campus the 2 days before the exam windows throughout the semester, in case you want to come by and actually talk to me in person about some problems that you're having going into an exam, or some things that you just want to go over. That's fine. So I'll be on campus for February the 7th from 4 to 6, February the 8th from 9 to 11. Also remember, I always have online office hours. You're always welcome to come by those hours. Sunday and Tuesday, 8:30 to 9:30 at night. Tuesday, Wednesday, and Thursday, 11 to noon. Always good times to come by and talk to me, and you usually can get individual help on problems, and that's a good time to get some help. Remember, you show up for my online office hours in the same place that you go to for lecture. Today, we're going to be continuing looking at applications of integration that we started last week. So we've talked about area between two curves. We've talked about volume using disks and washers. We've talked about volume using shells. So today we're going to be looking at lengths of curves, surface areas of solids of revolution, and one example or 1 or 2 examples, a very narrow look at the idea of work and how integration relates to the idea of work in physics. And if you don't know what work is, we'll talk about that when we get to it. All right, so we're going to go ahead and just jump into this and get started. Our first topic to look at today is the arc length of a curve. And so when I'm talking about arc length, like for example in this picture that I've got right here, the length of the curve between A and B is what we're interested in. So the length of the curve from x equals A to x equals B is what we are interested in. And so on the curve, we're looking at this piece of the curve from this point right here to this point right here, and we're looking at that curve along the graph of f and what its length is. And so this just continues the discussion of length that you've been looking at really in mathematics from very early on, where you're looking at length on a number line, length in the plane when you're using the distance formula, length on a circle when you're talking about arc length. All of those are ideas where you're looking at the length of something. And so we're extending that in Cal 2 to looking at the length of a curve along a function. Okay, and so that green arc that I've got drawn there is what we're looking at, and we're going to try to find the length of that. And so I've got a couple of line segments drawn here, and this is the idea behind, and I'm not going to go into all of the nitty-gritty details on this, but I'm going to go into some of it. I'm going to show you where the arc length integral comes from. And it's actually just an extension, believe it or not, just the simple old distance formula from algebra. The distance formula, if you remember in algebra, says that the distance between 2 points, the straight line distance, or the distance along a line segment between 2 points, is simply the square root of x2 minus x1 squared plus y2 minus y1 squared, right? That's all you're looking at. So we're going to use that distance formula up in this picture that I've drawn up here, and we're going to actually use the distance formula to derive or at least kind of come up with an informal derivation of the arc length integral and where it comes from. And then we'll do the same thing for surface area of volumes of revolution, or solids of revolution rather. And then after we've derived both of those forms, then we're going to tackle some examples of integrals and actually calculate lengths and surface areas. And then after that, then we'll finish up with a brief look at work today. So that's our agenda for the day, just more applications of integration. And as always, for those of you who are with me live today, in this case I've got Elba and Jaime, and so hopefully both of you people can hear me. And don't hesitate to stop me along the way. If you have a question about something, I will be happy to go back over something or explain something in more detail if you have a question. So don't hesitate to stop me, okay? All right, so in this case, we're looking at the distance formula, and what I want to do is I just want to look at the distance between these 2 points right in here on this picture. This would be, I've got the interval split up into 3 regions, but the idea is that we split it up eventually into n regions, and this would be the ith region inside that arc right here. And we've got all these little line segments, and what we're going to do is find the length of one of these little line segments. And then after we look at the length of one of these little line segments, then we're going to talk about the idea that we add them all up and then let the number of line segments become arbitrarily large. And if we let the number of line segments become arbitrarily large, then remember we're talking about a definite integral when we do that. The limit of that Riemann sum is what we're talking about. So the distance that we'll call d sub I for that one little line segment right there, right? And that one little line segment we're saying approximates the length of the arc between those 2 points. So we'll call that d sub I. So d sub I, just using the distance formula, would be x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared, like that. Okay? And, that's straight from the distance formula. And what are you doing? You're subtracting x's and you're subtracting y's. And so what you're really doing is you're looking at the change in x and the change in y. So what we'll say here is we'll say that this is delta x sub I, and that delta x sub I simply means the change in the x in the ith interval in there. And we'll say the same thing for the change in y's right here, that this would be the change in y sub I squared, like that. And so we get that little expression for the distance of that ith line segment right in there. Now what we could do is we actually manipulate that a little bit, that little calculation right there. And what we're going to do is we're going to factor out delta x sub I from that quantity. So if we factor out a delta, delta x sub I squared. So if I factor out a delta x sub I squared, just pull it out of the region, or of the expression, then in the first term we just get a 1 because you're taking out that whole term. And in the second term, you get delta y sub I over delta x sub I, like that. And both of those are squared. And if if you're not sure about that, you can just multiply through by delta x sub I squared, and you can see how everything cancels out. And it's really the same expression. Okay, and so then what you do from there is, you can take the square root of that delta x sub I squared. Let me move this b out of the way here a little bit. That's b right there. And so you have the square root of 1 plus, and this would be delta y sub I over delta x sub I, and we'll go ahead and square the whole fraction like that. And then we take the square root of the delta x sub I squared, and we get delta x of I on the outside. Delta x would have to be positive, and so the square root of delta x of I squared would be just delta x of I, like that. And so we get that expression for the length of that ith line segment in there. Okay, so now remember what we do. Then if that's the length of one of the line segments, then what we do is we get a similar expression for all the other line segments, and then you add them together, and then you take the number of line segments and you let it become arbitrarily large. And when we do that, we come up with this integral right here. We come up with the integral s equals the integral from a to b of the square root of 1 plus dy dx quantity squared dx, like that. And you can see where that integral, and I'm skipping quite a few steps in here, there's no question about that. I said this is going to be kind of an informal derivation. But remember, we ended up with this approximation right here for that ith interval, the arc on that ith interval. That's the length of that line segment in there. And then from that, we're making the jump to this integral. But you can see how the form emerges in our integral down there. And remember, what we really did is we just added all the little line segments up and let the number of line segments become arbitrarily large. And when we do that, we're talking about taking the limit of a sum, of a Riemann sum, and we go from this summation problem to a definite integral. Now this form that I just wrote down is if you're given y to be a function of x. Now on the other hand, if you're given x to be a function of y, function of y right there, then this form becomes a little bit different. It would be the integral from a to b. Now the a and b values would now be y values. And this would be the square root of 1 plus dx dy squared and then dy. Right? Dx dy is just the derivative of x with respect to y instead of the derivative of y with respect to x. And so depending on how the function you're given is written at the beginning, you're going to use one of those two forms. So these are the arc length integrals right here that we will be looking at. Now, we will be returning to arc length later in the semester. This is not our only look at arc length on a curve. We will be looking at curves that are written differently in different forms later in the semester. We'll be looking at polar forms, and we'll be looking at parametric forms. And so later in Cal 2, we'll come back to arc length, and we'll actually write down some more forms for those that are based on these forms right here. But for finding lengths of curves where the curve is written in a different way, whether the curve is either written as in parametric form or whether it's written as a polar curve. Okay, if you'll just pause for just a second, let me go ahead and send a quick text here to a student who's new today. Okay, so there's our arc length integral. So we've kind of gone through kind of an informal derivation for the arc length. And so what we're going to do is we will look at some examples of arc length in a few minutes. All right, I want to, at the same time we've done arc length integrals, I want to turn our attention to surface area integrals. And hold on real quick, I think I've got my pages slightly out of order here. Let's only move some stuff around. There we go. Now I'm going to go to this page. All right, so surface area. Elba, can you hear me? Elba, can you hear me? All right, so in this case, what we're doing is we're talking about a solid of revolution like we were doing for volume problems. And so since we've got a solid of revolution, remember what we're doing is we're taking a curve and we're either rotating it around the x-axis or rotating it around the y-axis. So here I have this curve f, and I'm going to take that curve f and I'm going to rotate it around the x-axis. And what I've done here is I've drawn the surface that you'd be generating that's in the first quadrant. I haven't drawn all of it. I've just drawn the first quadrant piece right here. And so what we're going to do is we're going to look at what happens here, how we come up with the integral for surface area, right? And the way to look at this is, very informally, but is if you take a little line segment right there at the end of that curve, notice, and what you're doing is you're rotating that line segment all the way around the curve. And the length of that rotation is simply the circumference of a circle. And so what you're really doing here for surface area and the surface area integral, by the way, we usually write the capital letter S for, it'd be the integral from A to B, and this would be arc length, because it'd be the length of that little incremental piece of the curve right there. So it'd be arc length times circumference, because circumference is the distance that that little incremental piece traveled around the circle. So informally, this is what we're talking about. And I say informally, but really good to think about it this way, because if you get lost in a problem, you can always think about, okay, it's got to be arc length times circumference. And if I can get arc length times circumference, then I will be okay. So now put a little bit more into that formula. We have the integral from A to B, and circumference is easy. That'd just be 2 pi times the radius. And notice I have the radius drawn on my picture right here. Here's the radius of the rotation around the x-axis. So it'd be 2 pi times the radius, and then arc length, we're going to write this as a differential here, and this would be the differential of arc length. And this is sometimes just referred to as d arc length. And that's how I'm going to read that, as d arc length. D arc length means you're talking about a little incremental piece or a little incremental change in arc length. Just like dx is a little incremental change in x, dy is a little incremental change in y. So that's what you should be thinking about it. And so this little form, this would be our circumference piece right here, and this is our arc length piece right here. And then we simply just substitute what arc length is, and we know what it is based on the previous integrals. And by the way, make sure you understand that this is a capital S for surface area and a small s for arc length. And I know that's kind of confusing, and I've always thought it was confusing too, but that's the standard notation, so we'll continue to use that. So the capital S is for surface area, little s is for arc length. Okay, so this would be the integral from A to B, and this would be 2 pi times, in my picture that I've got right here, r would be equal to y. So this would be 2 pi times y times ds, d arc length, and d arc length would be, if y is given as a function of x, would be what we just wrote on the last page. It'd be 1 plus dy dx squared dx right there. And notice that since y is a function of x, this entire integral, that expression would all be in terms of x right there. And so that would be the surface area integral if you're given y to be a function of x. Now, on the other hand, if you're given x to be a function of y, for my picture up here, then the surface area integral would be the integral from A to B, but now A and B would be y values, and this would be 2 pi. And notice if it's you're given x as a function of y, but it's still a rotation around the x-axis, so this would still be 2 pi y times the square root of 1 plus, and then this derivative would change, and this would be dx dy squared dy, like that. Notice the y, the radius, is the same, regardless of whether the curve is given as a function of x or if the curve is given as a function of y. It doesn't matter. And so there's actually multiple ways that this could be written as far as the arc length integrals. And I've just written 2 of the possibilities right here. There are other possibilities also. What you need to do is you need to keep in mind this general form right here. I think this general form is a good way to get yourself through a problem. Think about it as 2 pi times the radius. So you draw the picture out and make sure you know what the radius is. And then d arc length. And d arc length does depend on whether it's y as a function of x or x as a function of y. And that will just change the radical that's part of the integral there. Okay, so these are what we call the surface area integrals. So I'll label it like that, surface area integrals. And with surface area, we will definitely return back to surface area in Cal 3. In Cal 3, we'll be looking at three-dimensional objects that are a little bit more general than these solids of revolution. And so we'll return back to surface area then and look at some more general forms for tackling that problem. So, okay, so those are the integrals. We've derived the integrals now. And so now what we're going to do is jump into some problems and work some problems out and see how this works. And if either of you have any questions that are with me live today, please shout out. So Jaime, you can hear me and I can hear you, so don't hesitate to stop me if you have a question. And Elba, I think you can hear me, but you can't talk for whatever reason, audio-wise. So you can chat me a question. That's always okay to do, and I will stop and try to answer your question. That's always okay. All right, so we are now going to tackle some examples. So this is our first example right here. So example, let's say we're given this curve, y minus 1 cubed equals x squared. And you may or may not know what that looks like. It's not x as a function of y or y as a function of x at all. And so we'll have to tackle a little bit on this as far as vaguely maybe what it looks like. And so the directions here are going to be find the length of the curve on the closed interval from 0 to 8. And so those would be x values right there. And so all you're doing here, if x is 0, you're substituting x equals 0 into the equation, and you get y minus 1 cubed is equal to 0. And so you get y is equal to 1 in that case. And so that would be the point 0, 1, right? And when x is 8, you just simply substitute 8 in there, right? So you get y minus 1 cubed is equal to 64. And then you take the cube root of both sides, and so you get y minus 1 is equal to 4, and so you get y is equal to 5. And so that would be the point 8, 5, like that. And so we have the curve, and we, ultimately, as long as we know that this is a continuous curve, we really don't have to worry too much about the specifics about the graph. We just know that we're talking about taking a graph, let me shorten this just a little bit here, that goes from the point 0, 1 to the point 8, 5, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5 right there. And so you're talking about some kind of a curve that maybe goes something like that. Right, and so we have this point right here, 0, 1, and this point right here at 8, 5. And we're talking about trying to find the length of that curve here. All right, so the first thing you need to do, if you're thinking about the arc length integrals, and I'll shift back to the arc length integrals for a minute. Here is which one of these forms are we going to use? Well, you need to know whether you've got y to be a function of x or x is a function of y, right? As far as which one are you going to use. And another way to look at this is, are you going to integrate with respect to x or to y, right? And that really kind of depends on the problem. In some cases it might not matter which way you go with this. In my problem, what I'm going to do here is I'm going to go ahead and solve for x. If I solve for x, so if I solve for x here, I get x to be plus or minus the square root of y minus 1 cubed, or x is equal to plus or minus y minus 1 to the 3/2. Now, this might look bad at first, but you have to kind of stick with it for a second and see how this turns out. And you may run into a roadblock as you go through this, in which case that would tell you integrate the other direction and solve for y in terms of x and integrate with respect to x. But I'm going to try to integrate with respect to y, and the reason why I know I'm doing that is I've solved these equations for x to be a function of y, right? And so I'm going to get an integral that involves y here. Now, in this particular problem, we're only looking at an x value that's positive here, and so I can choose the positive of these two roots here and just look at x to be y minus 1 to the 3 halves, like that. And so my arc length integral that we just wrote down a second ago is going to be the integral from, and what are you going to do here? You're going to look at the y values, right? And so this would be the integral from 1 to 5, because we're going to be integrating with respect to y. And this would be the square root of 1 plus dx dy squared dy. In other words, we're talking about the derivative of x with respect to y. So, okay, so let's see what that's going to be. I have x to be y minus 1 to the 3 halves. So dx dy, the derivative of x with respect to y, that's an easy chain rule problem. That would be 3 halves times y minus 1 to the 1 half, and then times the derivative of the inside, which is just 1. So easy enough, the dx dy is equal to 3 halves times y minus 1 to the 1 half. And now, if you're keeping an eye on the integral, what you now need to do is you now need to square that expression. So dx dy squared would be 9/4 times y minus 1 to the first. And again, y has to be positive here. Certainly it's greater than 1, or y has to be greater than 1 rather, and so y minus 1 is positive. So when you square that, you're just going to get y minus 1. You don't have to worry about anything going on here. Right, the square of a square root means you end up with what's underneath the expression. So dx dy squared is just equal to 9/4 y minus 9/4. Not too bad. And so you can come over to our integral now, and in place of dx dy squared, right, we have the quantity we just derived. So this would be 1 plus, and this would be 9/4 y minus 9/4 underneath the radical, like that. Okay, and then go ahead and you know that 1 is 4/4, right? And so you can collect like terms under the radical, and you get the integral from 1 to 5 of the square root of 9/4 y minus 5/4. And that'd be dy. Now, that is simply, if you think about this for a second, and we'll go through maybe a partial little piece of the substitution here, but if you think of that as a u substitution problem, you have u to be 9/4 y minus 5/4, and so then du is just going to be 9/4 dy. And so I can put in a 9/4, and then that gives me a 4/9 on the outside of the integral. And so that's all I have to worry about there, is that I end up with a 4/9 on the outside of the integral when I find that antiderivative. And so this is going to be 4/9 times, and remember, this is the square root of 9/4 y minus 5/4 is 9/4 y minus 5/4 to the 1/2 power. So remember, you're using the power rule here to integrate. So what do you end up with? You end up with 9/4 y minus 5/4 to the 3 halves, right? Adding 1 to the exponent, and you end up with 2/3 out in front, like that. And so then this would go from 1 to 5. And so our arc length would be 8/27. And then you get kind of a messy expression on the inside there. So let's see, if you put in 5, you get 45/4. So you're putting in 5 there, so you get 45/4 minus 5 fourths, 45 fourths minus 5 fourths would be 40 fourths, or 10. So I think I did that right. Right, if you're putting in 9 fourths times 5 minus 5 fourths, let's just go back through the arithmetic there to make sure I've got that. So that's 45 fourths minus 5 fourths, and so that's 40 fourths, or 10. And so the first part is going to be 10 to the 3 halves. And then the lower limit, you put in 1 for y, and you get 9 fourths minus 5 fourths, which is 4 fourths, which is simply 1. Right, so you get minus 1 to the 3 halves, which is just 1. And so that would be the exact value of the arc length right there. And then you could go through and use a calculator if you wanted a decimal approximation. Typically on exams, unless I specifically tell you, give me an approximation or give me an exact value, I'm not going to care too much about which way you write it. As long as it's correct, if you simplified the exact answer, I'd be okay with it. And so like this would be okay as an answer right here. It's not a bad idea to get a decimal approximation for it to kind of make sure that this answer actually makes sense in the context of the problem. And so let's see, if I did that really quickly on my calculator here, so I would take 10 and raise it to the 1.5 power, 1.5 power, and then I'd subtract 1, so I get that, and then I would multiply by 8 times 8, and then divide by 27 there, and I'm getting about 9.07 for that answer there. So as an approximation. And based on my picture, that's probably not too far from what makes, I mean, that certainly makes sense in terms of the graph right there. Right, so this is the exact answer right here. This is the approximation right here. And like I said, typically it's not going to matter to me which one of those forms you use. Either one would be fine. Okay, so what do we have to do at the beginning here? Let's kind of take stock of what we've done. We had to figure out which arc length integral we wanted to use. One arc length integral depends on y being a function of x. That's when you'd integrate with respect to x. And one depends on having x to be a function of y. Because the equation we were given at the beginning here was not written either way, we had to decide which way we were going to do this. Were we going to write x as a function of y or y as a function of x? Right? And so that's what I had to do, is I had to solve the equation for one variable or another. So I chose to solve for x. And so I took the square root of both sides of the equation and then kind of went from there. So that's what I was doing right in these steps right in here. So I chose to solve for x. I've got x to be a function of y right here. And because x is some function of y, then I'm going to integrate with respect to y. And that's the arc length form I'm choosing right here. And then over here, I found the derivative of x with respect to y, right, in that form, and then plugged it into our arc length integral, and then calculated the integral from there. Okay, so there is some work to do at the beginning of a problem like this. And arc length integrals, frankly, is a pretty easy problem. They can notoriously be difficult integrals when you're working through these kinds of problems. So, okay, so unless I hear somebody yelling at me to stop for a second, I'm going to go ahead and try another arc length problem. Okay, so this would be the problem we're talking about right here. So this is an example. Let's see, start here. Okay, so the example is find the length of the curve y equals x cubed over 6 plus 1 over 2x, yuck, from x equals 1 to x equals 2, like that. All right, so now notice in this problem, y is given as a function of x. So our arc length integral, first of all, is going to be the integral from 1 to 2, and this is going to be an integral with respect to x. We're going to have the square root of 1 plus dy dx squared, and then this would be dx. Right, that would be the form for our arc length integral here. Are we okay there? All right, and so then what we're going to do is we're going to first find dy dx. I do that off to the side. So I usually try to get all the little pieces to this arc length integral done off to the side, and then I bring them back into the problem. All right, so we've got y to be 1/6 x cubed plus 1/2 x to the negative 1. So I first want to write it that way if I'm going to find the derivative. And so dy dx, not a hard derivative, is going to be 1/2 x squared minus 1/2 x to the negative 2. All right, and now if you're looking ahead, what you're going to do is have to square this quantity, and it's kind of a yucky form for squaring right now. So this is a nasty form for squaring. Nasty form for squaring. And so I'm not going to do that. I'm going to try to change this algebraically a little bit. So I have dy dx. And so let me go ahead and factor out a 1/2 x to the negative 2. There is a 1/2 in both terms, and then there's x's in both terms. And remember, you always factor out the smallest power of x. So the smallest power of x there would be x to the negative 2. So when you do that, you're left with something that's not bad. This is just x to the 4th minus 1. Right? You took out a 1/2 x to the negative 2 out of both of those terms. And so you end up with x to the 4th minus 1. You could multiply that out to verify that that's what you get. And so this is x to the 4th minus 1 over 2x squared. Now you see, this paid off for me to do that because that's a lot easier to square. So dy dx quantity squared is going to be x to the 4th minus 1 over 2x squared squared. And so you get dy dx squared is equal to x to the 8th minus 2x to the 4th plus 1 over 4x to the 4th. Oh my gosh. All right, and so now if you think about the radical, if you're going up to the original problem now, you're looking at that radical. So if I underneath that radical is 1 plus dy dx squared. So this is 1 plus dy dx quantity squared would be 1 plus x to the 8th minus 2x to the 4th plus 1 over 4x to the 4th. Get a common denominator there, so that would be 4x to the 4th over 4x to the 4th plus x to the 8th minus 2x to the 4th plus 1 over 4x to the 4th. Oh my gosh, algebra is really horrible. And so now they have a common denominator. You add them together, and you do get like terms in the numerator. And so notice this gives me an x to the 8th plus 2x to the 4th plus 1, like that. Elba, I can hear you now.
Yeah, you hear me? Perfect. Thank you.
I can definitely hear you. Now, now that your sound is working, if you will, if you're not asking a question, go ahead and mute yourself, and then just unmute it. There's a button on there that's mute and unmute, and just mute yourself because we can get a lot of feedback from wherever you are. And then when you have a question, just unmute yourself, and then you can ask the question. Right? And you'll get used to doing that. So.
Okay, perfect. Thank you.
Thank you. We're glad you're here. Definitely, you're this is your first day with us, and so I'm glad you're here. Definitely. All right. So that expression right there is what goes underneath the radical. So we're going back up to this problem now, and we've got the whole thing under the radical done. This is the square root of, and this is what I just generated over to the right here. Now, there are multiple ways to go through the algebra on this problem. Let me warn you, they're all messy. And so however you want to go through the algebra is fine. But you want to be able to get to this expression right here. And then what happens is, this works out nice because the numerator ends up just being x to the fourth plus 1 squared over 4x to the fourth. It ends up being a perfect square. So notice what at first looked like it could be a horrible integral ends up not being too bad because it ends up being a perfect square and the radical ends up going away because all that expression underneath is positive. So when you take the square root, you can certainly do this and write it as just x to the fourth plus 1 over 2x squared. So it ends up horrible algebra, but after you survive the algebra, you end up with an integral that ends up not being bad at all. You end up with x to the fourth over 2x squared plus 1 over 2x squared. Remember, we've talked about this kind of integral before, where you have a single term in the denominator. Don't forget that you just divide it out term by term. And so our arc length integral ends up being the integral from 1 to 2 of 1/2 x squared plus 1/2 x to the negative 2. Almost the exact same expression we started with at the beginning of the problem. Very similar kind of the expression to the derivative. So the antiderivative ends up being easy, right? You end up with 1/6 x cubed, and then this would be minus 1/2 x to the negative 1, and this would be from 1 to 2. All right, and so let me clean that up a little bit. You get 1/6 x cubed minus 1 over 2x, and this would be from 1 to 2. So at the upper limit, you end up with, let's see, 8/6 minus, and then you end up with 1 over 4. There's the upper limit. And then minus the lower limit, which is just 1/6 minus 1/2. That's a little bit easier. So you end up with 4/3 minus 1/4 minus 1/6 plus 1/2. Those are all twelfths, or we can write them all as twelfths, I guess that's what I wanted to say. So this is 16/12 minus 3/12 minus 2/12 plus 6/12. So let's see, you end up with 13/12, 11/12, 17/12. And so what did we just find? That 17/12 is the length of that curve, x cubed over 6 plus 1 over 2x, from x equals 1 to x equals 2. So notice that the length of that curve is just a little bit more than 1. Actually, it's close to 1.5. And so certainly never a bad idea to say, well, I wonder if that answer makes sense. Does it make sense in the way the picture looks? And so if you are working a problem like this on a test or on a homework assignment or something like that, and you want to see whether that answer makes sense or not, then what you do is you sketch the graph of this function and look at it from 1 to 2 and see if that actually makes sense, that length, just a little bit less than 1/2. So I have x cubed, and then this is divided by 6, and then plus 1 divided by, put in parentheses, 2x right here, like that. And so I think I've got that correct, because the calculator is going to do order of operations, but I always like to make really sure that what I'm doing, let's try that again. And let's see. Well, I'm not really sure what in the heck just happened here. Let's try that again. Y equals x cubed divided by 6. So I'm going to put that in parentheses. X raised to the 3rd power, there you go, divided by 6. And then plus 1 over 2x. This would be plus 1 divided by, put this in parentheses, 2x, like this. Okay, so that's better. So there's our graph. And now remember, what we're doing is we're looking at the graph from 1 to 2. And so we're looking at this piece of the graph here that's from x equals 1 to x equals 2. And we're seeing if a little bit more than 1/2 would make sense in the context of this problem, right? And in this case, to me, we've kind of made ourselves feel a little bit better that this 1.5, about 1.5, would make sense from 1 to 2 right here. It's certainly not really big. It's not really small length, and so about 1.5 wouldn't be a bad approximation. It doesn't seem like to what we've got there. You could actually count boxes if you wanted to, and see if it makes sense in that context. That would certainly be okay to do. Okay, so we've made ourselves feel better by the graph that this actually makes sense for this problem. So not a bad thing to do with your calculator when you're doing problems like this. All right, so that's a second example for arc length. And so now what we're going to do is we're going to move on to look at some surface area integrals and surface area problems and see how these work out. All right, so next problem. What we're going to do is we're going to take this function, and I actually have the picture drawn here, so let me kind of skip ahead. We have this function, f of x equals 2 times the square root of x. Okay, so that is the function I have in red on this graph right here. So f of x equals 2 square root of x is this graph right here. And we're going to rotate it about the x-axis. So this is our axis of rotation, is the x-axis. And I'm looking at that graph from x equals 4. So here's x equals 4 right here. And then here's x equals 9 right here. Right, and we're rotating around the x-axis. So what I've done is I've done some of the rotation there, and I've shown what the surface would look like in the first quadrant. And what you'd be getting is you'd be getting this surface all the way around the x-axis, right? The same kind of surface here. And so what we're going to do now is we're going to look at surface area here and the surface area integral and see if we can write out the right integral here for this particular problem. So this one's going to, first of all, let's write out the surface area integral. And let me write that down, surface area integral. And this is just the very general form right now that we want to start with. Whoops. Not surface integral. Surface integral is an entirely different beast here. Surface area integral, there we go. So the surface area integral is capital S equals the integral. We're just going to say from A to B right now. From A to B of 2 pi times the radius d arc length, right? That's our general form that we wrote down a little while ago for the surface area integral. All right, now the radius is pretty straightforward in this problem because if you look at an approximating rectangle in here, right, or what the rotation is, how far the curve is away from the x-axis, and you get that distance right there to be the radius. And that distance would be given by y. Since it's a direct measurement from the x-axis to the curve, that would just be equal to y, and that would be equal to f of x, which is 2 square root of x right there, right? So that's our radius in this case, is 2 times the square root of x for this problem. All right, we are given that y is a function of x. And so since y is a function of x, in this problem, let's see, so since y is a function of x, the ds piece, the d arc length piece, is going to be the square root of 1 plus dy dx squared dx, right? Since y is a function of x. If x is a function of y, the derivative would be the other way around. It'd be dx dy, the derivative of x with respect to y, and it'd be dy, it'd be an integral with respect to y. All right, and so we are ready to write out what we need here. Then our arc length integral is going to look like this. It's going to be the integral from, and in this case it's going to be from 4 to 9 of 2 pi times the radius, and the radius is going to be 2 square root of x, and then this is going to be times this radical, and we're not quite ready to completely finish this radical yet. We have dy dx quantity squared, and then dx. And so there's our arc length piece right there. Now we do need to calculate dy dx and square it, right, and do all that stuff. So we got to do that off to the side. So we have y to be 2 times the square root of x, or 2x to the 1/2 power. So dy dx, the derivative of y with respect to x, would just be simply x to the negative 1/2 power, right? Because it's just a power rule. Bring down the 1/2 times 2 is 1, and then subtract 1 from the exponent. That's easy enough. And then dy dx quantity squared is going to be is going to be equal to, not plus, equal to x to the negative 1/2 squared, which is just x to the negative 1, or 1 over x. Right, so underneath the radical, you have 1 plus dy dx squared is going to be 1 plus 1 over x, or x plus 1 over x. And so finally, that's what I've got underneath that radical. I've generated that expression 1 plus dy dx squared, and I get x plus 1 over x. So that's not too bad. And so our arc length integral now looks like this. It's the integral from 4 to 9 of 2 pi times 2 square root of x. And I'm not going to simplify any of that stuff yet. And then the square root of x plus 1 over x. Now remember, you have to come up with something that you can actually integrate. And so, we're kind of limited to what we can integrate. And so you have to look at what you've got and say, well, is this something I can actually work through? Do I have the enough to deal with this? Do I have the techniques that would be okay for this problem? Now let's see what we got. Well, the 2 pi and the 2 can come out of the radical, or of the integral rather, and write out 4 pi out there, times the integral from 4 to 9, and then I have the square root of x. Now think about this though, that fraction is the square root of x plus 1 over the square root of x. And so look, this, if you're just a little bit careful with the algebra, boom, those go away. And you end up, sure enough, with something that ends up being not so bad. This is just 4 pi times the integral of, from 4 to 9, of the square root of x plus 1 dx. Wow, it ends up being a pretty simple integral. And, if you did a substitution there, if you let u be x plus 1, well, du is just dx. And so this integral just ends up being, the square root of u du. And so it just ends up just being a power rule problem. So that ends up working out really nice. We have the 4 pi, and then since it's a power rule, we have x plus 1 to the 3/2, right? Because it was x plus 1 to the 1/2. And then you put a 2/3 in front. You always put the reciprocal in front. And then this would go from 4 to 9, like that. And so you end up with 8 pi over 3 out front. And then when you put 9 in, you get 9 plus 1 is 10. You get 10 to the 3/2. And then put in 4. 4 plus 1 is 5. And you get minus 5 to the 3/2. And please, if you've gone through all this heartache on this problem, and there's a lot of heartache on this problem, but and then you get down to the end and you tell me 10 to the 3/2 minus 5 to the 3/2 is 5 to the 3/2, you're going to be mad because that's a simple, algebra or arithmetic mistake. 10 to the 3/2 minus 5 to the 3/2 is not 5 to the 3/2, right? You can't combine those using rules of exponents at all. So that's our exact answer, like I've got right there. And then you could certainly find a decimal approximation if you wanted to. Now the units on that, this is surface area, so it's area, and so technically this is units squared right here. And so if you check in your answer in the back of the textbook, in our textbook, you'll find that they'll always write units squared or units, something like that, at the as part of their answer. I will not penalize you if you do not write units squared, but that's kind of a danger. I really should be maybe making a bigger deal about that. I just don't want you to lose sight of the fact that this is an area problem. It's an area of a three-dimensional object. It's a surface area, so it's the area of the outside of it. But it's still just an area problem, and so you should end up with square units as your answer there. Okay, so that's kind of a fun problem, I think. So now we're going to, let's see, I'm going to just do a little bit of a rearranging of my notes here, move some pages around. So there we go. So now look at it, and nobody's shouting at me, so I'm gonna keep on going unless somebody shouts at me. We want to look at another surface area problem. And so this surface area problem, we're given y to be the cube root of x plus 2. And this is from x equals 1 to x equals 8. And we're going to spin that curve, or rotate that curve, spin around the y-axis in this problem. Okay, so this is a little bit of a difference here. And so what we want to do is see what's going on when we spin around the y-axis, how that's going to change how we write out the arc length integral, and it is going to change it. It change a little bit about what we do here. In particular, it's going to change the radius. So we're talking about from x equals 1 to x equals 8. And so let's see. Let's go ahead and say that there's our x-axis, there's our y-axis like that. And I want to kind of see if I can fit the scale on here a little bit better. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to take the time to draw kind of a big picture here. And so when x is equal to 1, what happens here? When x is equal to 1, y would be the cube root of 1 plus 2, or 3. Right? And so you get the point 1, 3. Okay, so let's see, there's 1, 2, 3, 4. So 1, 3 would be right here. And then when x is 8, I end up with y equals the cube root of 8 plus 2. The cube root of 8 is 2, plus 2 is 4. And so I get the point 8, 4, which is right there. All right, and this is a cube root graph, and so the curve is going to just look something like that. It's a pretty subtle curve right here. Now remember, what we're doing is we're taking this and we are rotating around the y-axis. So we get a cross-sectional piece that's over like that, and the rotation, remember, is around the y-axis. So it's kind of like, you've got this circle right here, right? And you're rotating, and you would be doing the same thing on the other point also. It's much harder to draw, and I'm not going to do that here. The rotation, since it's around the y-axis, when you're looking at a representative little rectangle here, well, that might look like that. And that would be our r right there. That would be our radius. So notice in this particular problem, the radius is measured from the y-axis, and so the radius is equal to x, like that. Right, and so, how are we going to write out this integral is going to be the question. So, all right, so let's see how this works out. So we write out our surface area integral. And we want to write out the general form first. So capital S equals the integral from a to b of circumference, so that'd be 2 pi r times, or circumference ds, d arc length. Right, and so we have to worry about what d arc length would be in this problem. Y is given as a function of x, and so d arc length is going to be, using that form, ds is going to be the square root of 1 plus dy dx squared dx. Right, that's going to be our ds, our d arc length right here. And then r is going to be equal to x, like we have in the picture here. So this is a little bit more specific of a form now. So we're making some progress on this form. All right, so now what do I need to do? I need to find dy dx. Now I know, let's see, that y is x to the 1/3 plus 2. So dy dx is going to be 1/3 x to the negative 2/3. And so that would be 1/3 to the 2/3. And so dy dx quantity squared is going to be, what, 1/9x to the 4/3. And so 1 plus that would be 1 plus dy dx squared, or 1 plus 1/9x to the 4/3. And then you can get a common denominator on that. And so you get the expression underneath the radical to be 9x to the 4/3 plus 1/9x to the 4/3. All I did here is I got a common denominator, which is 9x to the 4/3, to add those two things together, those two fractions. Okay, so our integral here, our arc length integral now more specifically, would be the integral from 1 to 8 of 2 pi x times the square root of that really ugly expression, 9x to the 4/3 plus 1/9x to the 4/3 dx, like that. All right, so now the denominator there, I can take the square root of that. A lot of algebra in these problems, so you really have to watch it. And what I would do, you know, is I would kind of go back through these notes and see if you can figure out and reproduce the algebra that I'm doing on each of these steps. Make sure you know what I did in each one of these steps, because you're going to have to, frankly, on one problem on the exam on these, you probably will end up with confronting something where the algebra is pretty nasty. So you just got to be able to work your way through it. No way to avoid that, by the way. You're in algebra, or in Cal 2, the algebra is going to really be trying in some cases, really messy. All right, so I've got the constants are 2 pi and 3, so I'll take both of those out, 2 pi over 3. And then this would be the integral from 1 to 8 of x. And notice, by the way, well, I'll go ahead and write, let me take another, I'll take 2 steps to do this. I'll have x times this square root, 9x to the 4/3 plus 1, and then in the denominator, I just have x to the 2/3. And so notice if you subtract exponents on those x's, which would be okay to do, then you end up with x to the 1/3 on the outside of that radical. So you end up with x to the 1/3 right here, and then times the square root of 9x to the 4/3 plus 1 dx, like that. And actually, let me go ahead and write that radical, not as a radical anymore, but let me write it as a fractional exponent. So this is going to be 9x to the 4/3 plus 1 to the 1/2 power dx. All right, so let's see how this works out. This would be, you know, kind of a classic U substitution problem here. And so if I let U be 9x to the 4/3 plus 1, then du would be 36/3 or 12 x to the 1/3 dx. See, and look, I've got the x to the 1/3 there. So this is going to end up working, believe it or not, that I could be able to deal with this as a substitution problem. You'll have 2 pi over 3 times, and I'm going to leave a space, and then multiply by 12 on the inside of this radical. And then since I'm multiplying by 12 on the inside of the radical, I multiply by 1/12 on the outside. And remember, we've talked about that before. If you multiply by a constant on the inside of the integral, that's always legal to do as long as you multiply by the reciprocal on the outside, because it means you really haven't done anything at all. All right, so let's see, what does that give me? That gives me 2 pi over 36, or pi over, let's see, let's make sure that I've got all that correct there. So I've got 2 pi over 3. And I'm just going through and making sure that I didn't make any kind of a mistake there. But yeah, that should be pi over 18 for sure. So, so that gives me S to be pi over 18 times the integral of u to the 1/2 du. Right, when you make the substitution there. And, you know, the limits of integration are from 1 to 8. And so if you wanted to, you could change those limits of integration. And in fact, what I'm going to do, though, is I'm just going to not even go over to u's. I'm just going to write the power rule out like I've got it. So this is going to be 9x to the 4/3 plus 1 to the 3/2 power, right? Because we're using the power rule. I add 1 to the exponent, and I put the reciprocal of that exponent out in front like that. There you go. And this is going to be from 1 to 8. That way I don't have to worry about changing the limits of integration there. And so at the outside, this ends up being pi over 27. And then on the inside, let's see, you've got 8 to the 4/3. I'm going to write that out just in the middle there. 8 to the 4/3 is the cube root of 8 to the 4th power, which is 16. Cube root of 8 is 2. 2 to the 4th power is 16. And then times 9, that's going to be 144 plus 1 is 145. So at the upper limit, you get 145 to the 3/2 power. And then at the lower limit, that one's easier. 1 to the 4/3 is just 1, times 9 is 9, plus 1 is 10. So you end up with minus 10 to the 3/2, like that. And believe it or not, that would be the exact form for the surface area of that solid that we're generating right there. So kind of a really ugly expression like that. So, all right, so gives you a little bit of a flavor for how you deal with arc length problems and how you deal with surface area problems. Notice in every case, I kind of wrote out the general form for the integral first, and then tried to build all the little pieces to that, and then filled in the gaps from there. So and work the problem. All right. We are now going to look at, you know, our not our last application. We're going to look at a bigger application on Wednesday, but we have one last application to look at today, and that's the idea of work. Now, you know, basically, what I'm going to say here, and I am not a big physics person anymore. And so I'm just going to say, so some of you may have a better understanding of work than I do, but it's the, to me, it's the energy that's expended when you displace an object. In other words, when you move something, work is being expended, right? When something's position in space is being moved, when you walk across the room, when you raise your arm, when you take your book and raise it up above your head, when you take water and pump it out of a pool, when you take a spring and stretch it out, right? When you take a spring and compress it, when you take a chain that's laying on the ground and you pull the chain up, or a rope and you pull it up off the ground. When you take a satellite and launch it from the surface of the Earth up into space. All of those are wildly different examples, but what do they all have in common? They're all moving something. And so when you move something, work is being expended when you do that. So for example, I do want to kind of mention here, and I'll mention this again in lecture, and I'll probably remind you of it on Remind also, because you guys are all science people. One way or another, since you're in Cal 2, you're some type of a science person. But you know, SpaceX is getting ready to launch their rocket called Falcon Heavy. Falcon Heavy is the heavy version of their Falcon rocket, and it is the largest rocket as far as thrust goes that has been launched from the surface of the Earth since the Saturn V was launching Apollo missions in the late 1960s, believe it or not. So, oh my gosh, 50 years ago, right? And we have not built a rocket that has more thrust than the Saturn V since then. And the SpaceX, the Falcon Heavy, is the closest that we will have gotten. And so they're going to test launch that later this week or early next week. And so that's something to be watching for, because that's another big step in the our kind of march towards landing or orbiting Mars with humans. And so the Falcon Heavy is going to be kind of a stepping stone to that. I think the Falcon Heavy is going to be used to launch things eventually to the moon. And so be kind of watching for that and paying attention to that. And you're talking about a huge amount of work being expended to take something that's as heavy as it is and launching it into Earth orbit. You're talking about a large expenditure of energy to do that. And so a tremendous amount of work is needed to move an object like that for that distance. Now, work generally in a simple situation is simply force times distance. It's the force applied on an object times the distance. Now, we're only going to be talking about linear motion at this point. Later, you'll be talking about what happens, when you apply a force and the object's moving in a different direction than the force is being applied, which could easily happen. But we're not going to be doing that here. We're going to be looking at a much more simple situation, I guess. In the U.S. system of measurement, work is given in terms of foot-pounds. That's the most common unit for work in the U.S. system. In the SI system, the international system, work is given in Newton meters. And a Newton meter is abbreviated as a joule, Joule, and the abbreviation is just with a capital J. And that's an abbreviation for a Newton meter. The conversion between foot-pounds and joules goes like this, that 1 foot-pound is equal to about 1.35582 joules. You do not need to know that. You do need to know a little bit about what a joule is, that it's a Newton meter, and that in the U.S. system you're talking about feet and pounds. So the idea here is the distance we want to measure in feet, and if it's in the U.S. system, and if it's metric, we want to measure it in meters, right? That's what we want to talk about. All right, we are going to look specifically. We're not going to look at a lot of examples here. We're going to look at one specific situation, and these are spring problems. And these are when we are stretching or compressing a spring. Stretching or compressing a linear spring. Spring does not have to be linear, but you have something called Hooke's law for a linear spring, for a spring in general, and that is that force is proportional to the distance moved. All right, so F is equal to K times D. All right, and so a lot of times, and so in other words, for a particular spring, this constant of proportionality, you have to know that in order to write out the problem. The proportion constant. It's sometimes, and let me abbreviate, it's sometimes just called the spring constant. And that's the better way to say it. It's the spring constant. And you have to be given enough information to actually calculate the spring constant. Now, if the force is variable, so like in the case of a spring, if you think about it, if you're stretching a spring, what happens? As you move stretch the spring the first inch, well, you're going to need more force to stretch it an inch further on down, right? So in other words, from going from 0 to 1 inches as far as the stretch goes and going from 9 inches to 10 inches, well, you're going to need more force for the 9 to 10 inches than the 0 to 1 inches. So this is a variable force that's required to stretch the spring a certain distance. And so because it's a variable force, we actually have to use an integral to evaluate or find the force. And it's a simple integral, actually. It's the integral of the force function dx, where the stretch is from a stretch of A units to B units from the natural length of the spring. All right, so let's look at a problem here, and we'll look at two problems here. These will not take too long to do, and then we will be done with the day. And we'll have gotten a lot done, definitely. All right, so let's say that we've got a force. So this is an example. Let's say we have a force of 250 newtons, stretches a spring 30 centimeters. All right, and so what we want to do is find the work required to stretch the spring from 20 centimeters, a 20 centimeter stretch to 50 centimeters. All right, so this is what's going on here. This is one way to look at this. If here's our spring like this. Here's this, let's say it's hanging from the ceiling, right? That's the natural length of the spring right there. This is what we call the natural length. No force at all on the spring. And then what do? We attach a weight to the spring, and that weight exerts a force of 250 newtons. And remember, a newton is a kilogram meter squared per second squared. And so if we apply a force of 250 newtons, in other words, we attach a weight to this spring, right? And what happens? It stretches it 30 centimeters. And so what we want to do is we want to calculate the work that's going to be expended to stretch the spring from, not from its natural length, but from 20 centimeters longer than the natural length. So a stretch total of 20 centimeters like that to 50 centimeters like that. So we're going to stretch it 30 centimeters more, right? Basically is what we're talking about doing. So that's what we're after here. So now notice everything's given in centimeters here. We need to do these things, everything in meters. So first of all, 30 centimeters is 0.3 meters, right? So make sure that you write that down or don't overlook that. 20 centimeters would be 0.2 meters. 50 centimeters would be 0.5 meters. We need to do all this in meters if we want the answer to be joules at the end. So what do we have? We have Hooke's law that states that force is proportional to the distance stretched. Right, so what do we have here? We have 250 is equal to K times X, and that's we know that a 250 Newton force stretches the spring 30 centimeters, or 0.3 meters. And so we get that little calculation right there, which is easy enough. And so you get that K is equal to 2,500 over 3 when you do that. And so because K is equal to 2,500 over 3, what do we have? Our force function, f of x, is going to be 2,500 over 3x. Pretty simple function. And so the work to stretch the spring from a 20 centimeter stretch to a 50 centimeter stretch would go like this, that the function we'd be integrating would be 2,500 over 3x, so a super easy integral. And what are we doing? We're stretching it from 0.2 meters to 0.5 meters. And so those would be the limits of integration in this case. X would go from 0.2 to 0.5 if X is the stretch that you're talking about here. So pretty easy integral. And so you end up with 1250 over 3x squared, and that goes from 0.2 to 0.5. And so you get 1250 over 3 times 0.5 squared minus 1250 over 3 times 0.2 squared. And when you do the calculations, which I've already done, you end up with approximately 87.5 joules. And that's our the work required or expended to stretch the spring those 30 centimeters like that. All right, so this would be very typical kind of test question over work, to be honest with you. So, all right, so let's. We are now down to one problem left. One problem, and this one I've actually taken out of your textbook. This is problem number 236 in section 2.5 of your book. So, so this is, let's see, let's flip the screen here. Excuse me. And so this is section 2.5, and this is problem number 236. Right, and it says a 1 centimeter spring, I'm sorry, a 1 meter spring, a 1 meter spring. So in other words, the natural length of the spring is 1 meter. A 1 meter spring requires 10 joules to stretch the spring to 1.1 meters. So in other words, 1/10 of a meter. So the question is, what is the work required to stretch the spring from 1 meter to 1.2 meters? All right, so what did we do? We had 10 joules. That work would get us from 1 meter to 1.1 meters. And then what we want to do is look at the work to go from 1 meter to 1.2 meters. Now, so the stretch is twice as much, but this is a linear spring, so what's happening? As we stretch it, it takes more and more work to pull the spring or to stretch it, okay? So I want you to be careful about the fact you're just not doubling this. That's not the way this is going to work. Now, also notice, we've got to find the K value, find the spring constant, but we're given different information in this problem. We are not given the force that was required. We are given the work. We were given that work was 10 joules. And so to find K, we have to start with our integral, our work integral. Right? We have our work integral is force times force dx. And force is K times x dx. And what was our work? Our work was 10 joules. So we know the answer to this integral. Right? And so let's see, what are we going to do here? We're going to, let me write in the limits of integration. The limits of integration are that we would stretch the spring from its natural length, right? 1 meter is its natural length. And we are stretching it from 1 meter. So it's a stretch of 0 meters to 0.1 meters, right? That's the range on the stretch here. And we can do this even though we don't know the K value. Notice that we can find K from this calculation because the integral is just 1/2 kx squared from 0 to 0.1. Right? So it's actually a relatively easy calculation here. So you have 10 joules is 1/2 times K times 0.1 squared. Lower limit would be 0. So you have 10 joules is 1/2 K times 0.01. And so if you do the calculations there, you end up with k to be 2,000. All right, you end up with k to be 2,000. All right, so what does that give us then? That now we can write out the integral for our problem. The integral for our problem would be our force would be f of x is equal to 2,000x, because k was 2,000, right? Remember, force is equal to kx. K is 2,000, so force is 2,000x. So that's the function we're integrating. And then we would integrate that from 0 to 0.2. We're doing a stretch of 0 meters to a stretch of 0.2 meters. So again, pretty easy integral. The problems I'm going to look at, the integrals will not be hard. And these are both these very typical kind of test questions, what I've just written down. On the test, you'll have one problem like this, very similar to what we've just done. So work would be 1,000 times 0.2 squared. Work would be, 1,000 times 0.04. And so you end up with work to be 40 joules. So notice we stretched the spring twice as much, and we expended 4 times as much energy to do that for this spring. All right, a different spring constant, and you'd have a different ratio there. Okay, so let me just tell you that homework due on February the 4th. This is your first assignment, and that is going to be on section 2.4 of your book. Let me make sure that I've write down the right problem and section number here before you leave. Yes, this is section 2.4, and this is problem number 176. And you will find that that is very similar to a problem we did in lecture today. So, all right, so been through quite a few examples. We've been through 3 more applications. Next time, we're going to look at one more application that will take us the entire class period to get through. It's called center of mass. And then we'll be through with the applications we're going to do for now. And then we'll turn our attention to techniques of integration and start looking at integrals more carefully. So for any of you that are with me today live, or does anybody, I know I've been through, nobody said anything as we went through this, so I worked steadily through this. Does anybody have any questions before we shut this down for the evening? All right, so then no questions. Then everybody who's with me live, you guys have a good evening. And those of you who are watching this recorded, have a great week. Please don't hesitate to come by my online office for help, or to email me, or to send me a remind message for help. You have lots of ways of contacting me, and I'll be more than happy to help you out. Everybody have a great day and a great week.